All right. So in section 7.7, we're talking about complex numbers. Introduction. In the previous sections, we learned that the even root of a negative number is not a real number. In this section, we will define a new set of numbers by including the real numbers and the square roots of negative numbers. While these numbers may be difficult to visualize, they are solutions to equations that have applications in engineering and electronics. So complex numbers are important because they do actually somehow pop up in real life and help us in engineering applications. All right, so what is a complex number? My simple definition of it is we're going to take a real number and add or subtract from that an imaginary number. And you're like, what on earth is an imaginary number? We use I to denote the imaginary numbers, and we define the number I as follows. Okay, so an imaginary unit, I, is defined by I squared is equal to -1, and I is equal to the square root of -1. Okay, so we have this number I that equals the square root of -1. Okay, or I squared equals -1. And if we use that, we take multiples of I, like 2I, 3I, 4I, and add or subtract that to any of our whole numbers. So 5 plus 2I, -6 minus 5I. Those are called complex numbers. Okay, so what are pure imaginary numbers versus complex numbers? A pure imaginary number is a number that is only imaginary. It doesn't have any real part. So it's just I multiplied by some real number. Okay, I times a real number would be a pure imaginary number. Now that we have this definition of I, this allows us to take the square roots of negative numbers now. Okay, how are we going to do that? Using this, the square root of -b is equal to the square root of b times I, or I times b. Why does this work out? Just really quickly, let me pick any old number. Let's say we want the square root of -3. Well, -3 is equal to -1 times 3. We can all agree with that, right? And then if we break this up using the multiplication property of square roots, this would be the square root of -1 times the square root of 3. And then, what did we just say the square root of -1 is? By definition, the square root of -1 is this new number that we just came up with, I. It's an imaginary number. So we get I times the square root of 3. Now, anytime we take the square root of a negative number, we can simplify that to an imaginary number. Okay. All right. Example 1 goes through a few problems where this is simplified. All of the steps are shown the same way, but we can kind of go through this quickly. We know the square root of 25 is 5, so the square root of -25, that negative will give us an I, would be 5I. The square root of 81 is 9, so the square root of -81 would be 9I, because the I takes care of the square root of the -1 that's in there. The square root of -12, now we don't know the square root of 12, that we have to simplify that a little bit, but we can say that this is the square root of 4 times 3 times -1. The square root of 4 is 2. The square root of -1 is I, and then we still have a 3 under there. So we get 2I times the square root of 3. And we can kind of break down the square root of 27 that way. You can also just bring the I out in the beginning. We know the square root of -27 is going to be I times the square root of 27. And then break down the square root of 27 just like we did previously. That would be 27 is 9 times 3. The square root of 9 is 3. So we get 3I times the square root of 3. This almost simplifies the same way that it did before, except now we know that the square root of the -1 gives us an I that we can pull out as well. All right, let's jump into a few more practice problems with these. For practice exercise number 1, problem 1, excuse me. The square root of 36. This is an easy one. We know the square root of negative 36, I'm sorry. We know the square root of 36 is 6, so the square root of negative 36 would be 36i. And again, just to show this is negative 1 times 36. The square root of negative 1 times the square root of 36 would give us I times 6, or 6i. We usually write the real number first and then the imaginary part after. For part B, the square root of negative 49 over 121. Again, this is the square root of negative 1 times 49 over 121. The square root of negative 1 is I, and then the square root of 49 is 7, and the square root of 121 is 11. So we get 7 over 11i. You can also write this as 7i over 11, or however you want to combine the numerator. Next one, we have the square root of negative 108. Okay, 108. 108 is 12 times 9. So we're going to get an I on the outside. We can just put that there. And then we have the square root of 9 times 12. I can break that down a little bit more. Ooh, sorry. So when we are factoring numbers like 108, we want to try to pull out the largest perfect square. So the first perfect square that I thought of that's a factor of 108 was 9. But that's not the largest perfect square, because I get 9 times 12. 12 can be broken down somewhere also. 12 is 4 times 3. So the largest perfect square would have been 36. I didn't recognize that at first, but if I had, that would have saved me a step. So this is the square root of 9 times 4 times 3. All right. We already have our I on the outside. The square root of 9 is 3. The square root of 4 is 2. And then we're left with a square root of 3. So we need to combine that I times 3 times 2. That's 6i times the square root of 3. All right, last one, we have the square root of 20, negative 20 over 63. Okay, so we have negative 20 is 4 times 5. 63 is 9 times 7. All right, so we want to pull out the things that we can take square roots of. And you can think of that negative again as a negative 1. So we're going to get an I because it's a negative. For the 4 over 9, the square root of 4 is 2, and the square root of 9 is 3. So we get I times 2/3, and then we still have the square root of 5 over the square root of 7. And you can write it as one big radical if you want to also. Now, what's the normal order that we write these things in? Again, we usually write our numerical terms first, and then the i's second. So the proper way to write this would be 2 root 5 over 3 root 7 times I. Hopefully you recognize here that now, anytime when we take the square root of a term that involves a negative, it almost simplifies exactly the same way as it would if the number didn't have the negative, except because it does have a negative, we have an I included. And what I mean by that is, if I would have just asked you to take the square root of 49 over 121 without the negative, well, that's equal to 7 over 11. With a negative, 7 over 11i. The square root of 36 without the negative is 6. With the negative, 6i. All right, one problem down. So these are all pure complex numbers because they only have an imaginary part. Yes, it's multiplied by a constant, but it's only one term and it's an imaginary term. Okay, that brings us next to our definition of complex numbers, which we said verbally earlier, but let's look at it here. A complex number if it's written in standard form, is of the form a plus bi. A represents some real number, so it's a strictly real number. Something like 1, 2, 3, -5, 10, square root of 2, real numbers, and then plus b times I, some imaginary part. So a real part plus a complex part, okay? A and B are real numbers in the real part, and B is called the imaginary part. If B equals 0, then you just have a real number. And if A equals 0, you just have an imaginary number. If A and B are non-zeros, then you have a complex number. Okay, little note down here. Note, every real number is a complex number, technically. Okay, and that's because we just say that the real numbers are complex numbers where B is equal to 0. All right, fun stuff. Adding and subtracting complex numbers. So we can add and subtract complex numbers by adding and subtracting the corresponding parts. So add the real parts together, add the imaginary parts together, and then simplify. Same thing for subtraction. I'm going to jump to the practice problems here. So for something like 5i plus 4 minus 2i, you can think of this as how you would think about adding terms with x's, like terms. The imaginary terms are like terms. The constant terms or the real terms are like terms. So you can combine the like parts. Here, we can combine the 5i with the minus 2i. Okay, so you'd have 4 plus 5i minus 2i. Also, notice how I rearranged the terms. Technically, because addition is commutative, we can rearrange these almost anyway. But the standard form of a complex number has your real part first and then plus your imaginary part. So I just moved the real number to the front. All right, then this would be 4 plus 5i minus 2i is 3i. We leave our final answer this way. Real part plus imaginary part. For part B, 3 plus 4 minus 2i, we can add the 3 plus 4 together and then subtract the 2i. 3 plus 4 is 7. So this is 7 minus 2i. All right, part C has 2 imaginary parts and 2 real parts. 2 plus 7i plus 4 minus 2i. This would be 2 plus 4 plus 7i minus 2i. That's 6 plus 5i. And then if your second term is being subtracted, just be careful. We have to subtract each of these terms in the second expression. So this would be 8 minus 4i minus 2 plus I. Putting the real parts together, that's 8 minus 2. And then for the imaginary parts, minus 4i plus I. This simplifies to 6 minus 3i. So when adding and subtracting complex numbers, you add together the real part, or add or subtract the real parts and add or subtract the complex parts. And for your final answer, to write it in proper standard form, you want the real part first and then the complex part second. Some of you have probably seen complex numbers before, so hopefully this is a little bit familiar. If not, hopefully it's pretty straightforward. Once you get the idea that I is a thing, okay, and remember that it is equal to the square root of -1, then this kind of works out very similarly to how we've added and subtracted polynomial expressions previously. Next, we're going to talk about multiplying complex numbers, and this will work out the same kind of way that we multiplied before. You're going to use the distributive property and you're going to use foiling, okay? So if we have to multiply, let's see, our different examples here. We have an imaginary number times a complex number, 2i times 7 minus 5i. Then we have 2 complex numbers being multiplied. Then we have a complex number squared. Then again, 2 complex numbers being multiplied. But if you look at them, one is 3 plus 2i, the other one is 3 minus 2i. Before, when we had something like this, we call those conjugates. This is a complex conjugate. We'll define that next though. All right, for 2i times 7 minus 5i, we need to distribute the 2i to each of these terms. 2i times 7 would be 14i. And then 2i times 5i would be 10i squared. And then you're probably thinking, okay, we're done. 14i minus 10i squared. Remember I said there's a gotcha. How did we define I squared at the very beginning? Or how do we define I? Remember we said the square root of -1 is equal to I, which means that I squared, if we square both sides here, would be equal to -1. So anytime we see an I squared, we can simplify that a little bit. This would be -14 times -10. I'm sorry, this would be 14i, not negative. 14i minus 10 times -1. So I squared equals -1. And then if we simplify that, that's 14i plus 10. And then last thing, just remember in standard form, the real number comes first and then plus the complex number. So that's 10 plus 14i. Our thing to remember is that anytime we see an I squared, we can replace that with a -1. All right, let's do this. So for part B, we're gonna FOIL this out. 3 plus 2i times 4 minus 3i. We're gonna start off by multiplying the first two terms. 3 times 4, that gives us 12. And then 3 times -3i, we get minus 9i. And then plus 8i. And then minus 6i squared. So when we simplify this, we can combine the i's in the middle, the two middle terms. And then we also need to replace the I squared with a -1. So this is 12. And then -9 or minus 9i plus 8i would be minus I. And then minus 6 times -1. Okay, there's a little bit more simplifying that we can do. So we have 12 minus I, and then minus 6 times -1 would be plus 6. 12 plus 6 gives us 18, and then we have the minus I still. So 18 minus I. All right, part C, 5 plus 4i squared. Just a reminder, no matter how tempting it is, we cannot just square the 5 and square the 4i and call it a day. We have to FOIL here. This is 5 plus 4i times 5 plus 4i, which would be 25 plus 20i plus 20i plus 16i squared. So we get 25 plus 40i plus 16 times -1. So 25 plus 40i minus 16. All right, then last up, what's 25 minus 16? 25 minus 16 would be 9. So we get 9 plus 40i. All right, and last one, 3 plus 2i times 3 minus 2i. As I previously mentioned, if we look at these, both of them have the 3, both of them have a 2i. The only thing that's different is the sign. These are conjugates of each other. And when we multiply conjugates, nice things happen. We're gonna get, if we FOIL this, 3 times 3 is 9. And then we have minus 6i plus 6i. So those are gonna cancel. And then minus, be careful with this, 2i times 2i would be 4i squared. So we get 9, those cancel, and then minus 4 times -1. So that becomes 9 plus 4, which is 13. So all of the imaginary parts go away. because the two middle terms cancel out, and then the I squared is just a -1. So we end up getting a whole number. And then if we can take it a step further and say, not only do we end up getting not a whole number, but a real number, the real number could have been found from the beginning by just taking the fact that A, if we look at this as A plus BI, A is 3, B is 2. This is just A squared plus B squared. Yeah, B squared. 3 squared plus 2 squared equals 9 plus 4, which is 13. This pattern here happens every time that you multiply a complex number by its conjugate, okay? And that's what we're going to talk about next. So the complex conjugate, the conjugate of A plus BI is A minus BI. Pretty straightforward. And as we just showed, if you multiply a number by its conjugate, you just get A squared plus B squared. Okay, so for a complex number times its conjugate, it's just A squared times B squared. If I multiplied, let's just pick one, 5 plus 7i times 5 minus 7i, this is just going to be equal to 5 squared plus 7 squared. Which is what? 74. All right, that's going to be a good tool or formula that we can use and remember going forward. All right, let's jump down to our next group of problems. And the next type of problem we're going to be looking at, we're going to talk about dividing complex numbers. I'm going to put a star by this one because so far the operations have not been that bad. For adding and subtracting, you just add and subtract the parts that are alike. Makes sense? You add the constants or real numbers, you add the complex numbers. Subtract the real numbers, you subtract the complex numbers. Pretty straightforward. For multiplying complex numbers, it's been working out kind of the same as if we multiply polynomials. That's not too bad. We just have to remember that I squared equals -1, and then we can simplify a little bit more. Dividing is probably the hardest one because it's not instinctively something that we would think about doing. But once we learn the, not trick, but technique that we use for dividing complex numbers, then you'll realize this one's easy too. All right, so steps for dividing complex numbers. Step 1, write the numerator and denominator in standard form. So you want A plus BI over A plus BI. Okay. Step 2, multiply the numerator and denominator by the complex conjugate of the denominator. That is the key. So when dividing two complex numbers, we multiply by the conjugate of the denominator. And you have to multiply the numerator and denominator by the conjugate of the denominator. Then from there, in the denominator, if you multiply a number by its conjugate, it's kind of like what we did with rationalizing almost. When you multiply a number by its conjugate, the i's will cancel out. You'll just end up with a real number. And then in the numerator, you'll have some complex number. And you'll be able to simplify this into a real part plus a complex part. All right, let's just do one example here, and then we'll jump into the other practice problems at the bottom. I'll do the hardest one here. Let's do D. All right, so for problem D, we have 1 minus 3i over 2 plus I. These are already written in standard form, so there's nothing left to do there. Then to divide these, we're going to multiply by the conjugate of the denominator. The conjugate of 2 plus I would be 2 minus I. And we're going to do that in both the numerator and denominator. All right, let's go. In the numerator, remember that we have to FOIL. So we would end up getting 1 times 2 is 2, and then minus I, minus 6i, and then plus 3i squared. Okay, and the denominator, we have two conjugates being multiplied. A in this case is 2, B is 1. So this will end up being 2 squared plus 1 squared. You can also FOIL that out if you don't remember that rule. You would get 4 minus 2i plus 2i minus I squared, which is 1. Okay, anyway, from here, let me just simplify the denominator. 2 squared is 4, 1 squared is 1, so that would be 5. And in the numerator, we have 2 minus 7i plus 3 times negative 1. So 2 minus 7i minus 3 over 5. And almost finally, the 2 minus 3 gives us a negative 1 minus 7i over 5. And you might be thinking, cool, we're done. And we are almost done. The only thing is, this is not in standard form. The standard form of a complex number is the real part plus a complex part. So we can break this up into 2 different parts. We're going to take the negative 1 and divide by 5, and then minus the 7i divided by 5. So if you break this into 2 separate parts, we have negative 1/5 minus 7/5 I. That is our final answer. All right, we're going to jump to problem number 4, and then we'll almost be done. This is our last, well, we have 2 more topics. We'll do some practice problems with dividing, and then we're going to talk about higher powers of I, and then that'll be it. We'll stop. All right, for dividing, part A, negative 4 plus 5i divided by 2i. We're going to multiply here by the conjugate of the denominator. The conjugate of 2i is negative 2i. So we're going to multiply the numerator and denominator by negative 2i. That gives us, remember we have to distribute to both of these terms. So that'll give us 8i minus 10i squared in the numerator. And in the denominator, we'll just end up with 2 squared. But I'll multiply it all out just so that you can see. So we'll get negative 4i squared. Remember, I squared is negative 1. So this is 8i minus 10 times negative 1 over negative 4 times negative 1. So 8i plus 10 over 4. And then there's a couple things we can do here. First, we want to break this up into 2 parts. We also want the real part first and then the imaginary part second. And then we also can simplify this a little bit. All of those things need to be done. You can do them in whichever order you want. First, I'm going to rearrange the order. 10 plus 8i over 4. Then I'm going to break this up. 10 over 4 plus 8 over 4i. And then I'm going to simplify. 10 over 4 is 5 over 2. And then that's plus 8 over 4 is 2. So 2i. 5 over 2 plus 2i is our final answer. For part B, we have negative 7 over 3 plus 5i. The conjugate of 3 plus 5i is 3 minus 5i. We're going to multiply the numerator and denominator by 3 minus 5i. That will give us, in the numerator, negative 21 plus 35i. And in the denominator, when you multiply 3 plus 5i by its conjugate, 3 minus 5i, we just get 3 squared plus 5 squared. If you are not convinced of this, or you don't see how it works, FOIL it out, and after you do a couple of them, you'll start seeing that pattern. All right, so this is negative 21 plus 35i over 9 plus 25, which is 34. Yeah, that's right. Okay, and then last part, we want to break this up. So we'll end up with negative 21 over 34 plus 35 over 34i. And does that simplify? It does not simplify anymore, so we'll leave it this way. For part C, negative 2i over 5 plus 7i. We're going to multiply by 5 minus 7i in the numerator and denominator. All right, this gives us negative 10i plus 14i squared over 5 squared plus 7 squared. All right, then, do I believe me? Yeah. All right, so then this is negative 10i plus 14 times negative 1. After a while, you'll realize 14i squared is negative 14. After you do enough of these, you'll start noticing those patterns. You can simplify a little bit quicker. Oops, I forgot our denominator. Divided by 25 plus 49. All right, so we have negative 10i minus 14 over 74. Again, we do need to break this up, and we also need to switch the order so that the real part is first and the imaginary part is second. That's negative 14 minus 10i over 74. And I think we can simplify that a little bit. Everything's positive. So at the very least, we'll be able to divide by 2. So this is negative 14 over 74 minus 10 over 74i. And you could have simplified before you broke it up, or before you or rearrange the terms. So the simplifying and rearranging terms and breaking up into 2 different parts, you can do that in any order. I always just simplify last. All right, if we divide everything here by 2, we get negative 7 over 37 minus 5 over 37i. Last one, part D, negative 2 plus 7i times 3 plus 2i. Here we're going to multiply by 3 minus 2i in the numerator and denominator. And I just like to throw in my parentheses so that we can all remember we're foiling this. That gives us, in the numerator, negative 6 minus 4i plus 21i minus 14i squared. In the denominator, we'll end up with 3 squared plus 2 squared. All right, so that's negative 6 plus 17i, and then minus 14i squared would be a plus 14, because the I squared gives us a negative 1. And then it's over 9 plus 4, which is 13. All right, we're almost done. Negative 6 plus 14. Did I math wrong? I did math wrong somewhere. All right, I almost made it without a mistake. When you FOIL here, you get negative 6, but you should get a plus 4i. And then that will change this middle term to 4i plus 21i is 25i. All right. Now that we've got that, negative 6 plus 14 is 8. So we have 8 plus 25i over 13. And then we need to break this up. 8 over 13 plus 25 over 13i. And that's our final answer. Let's think about what happens when we raise I to different powers. We know that I is equal to the square root of negative 1. And we know I squared then would be equal to negative 1. Let me move that. Can't move it down. Move it down here. I equals the square root of negative 1. Then I squared would be equal to negative 1. Great. What is I cubed? I cubed is just I squared times I. We break it down. We know I squared is -1, and we know I is the square root of -1. So I cubed ends up being negative square root of -1. Just using the fact that I is the square root of -1 and I squared is -1. All right, and that leads us to the next power, I to the 4th. I to the 4th is the same as I squared times I squared, or you can think of it as I cubed times I. Either way, if we do I squared times I squared, that's -1 times -1, which is +1. Okay, so now we're back at 1. And then if we do I to the 5th power, that's I to the 4th power times I. Well, we just said that I to the 4th power is just +1. So what's +1 times I? I. So now we're back at I. Okay, and then I to the 6th, well, that's I to the 5th times I. I to the 5th was just I. I times I is I squared. So now we have another I squared. This is a cyclic pattern. If I write this a little bit more clearly, we started off with I, then we had I squared, then we had, then we had I squared, which is -1, then I cubed. So I cubed is -I. I to the 4th was 1, then I to the 5th was I again. I to the 6th was I squared, which is -1. I to the 7th would be the same as I cubed, which is -I. And then I to the 8th, if we did it, would be the same thing as 1, I to the 4th. And it just repeats over and over and over. So every 4 powers, we cycle over and over through I, -1, -I, 1. I, -1, -I, 1. And how do you figure out, like, let's say I had I to the, 57th power. I'm not going to write out I to the 57th and count over and over and over. We can use the fact that every multiple of 4 is going to be 1. And then after that, we have I, -1, -I. So we're going to divide by 4 and then use the remainder to help us figure out what power of I this will simplify to. Here, it's written a little bit nicer here, nicer font. So I to the 1st power is I to the 2nd power is -1, I cubed, -I to the 4th, 1. Every multiple of 4, I to the 4th, I to the 8th, I to the 12th, I to the 16th, I to the 20th, I to the 24th, I to the 28th, I to the 32nd, all of those will equal 1, okay? Every number that you divide by 4 and get a remainder of 1, so like 9 divided by 4, that's 2 with a remainder of 1. 13 divided by 4, that's 3 with a remainder of 1. All of those will be the same as I to the 1st power. You'll get I. Everything with a remainder of 2 will be equivalent to I squared, so that's -1. Everything with a remainder of 3 will give you I cubed, which is -I. And then you can't have a remainder of 4 because we're dividing by 4. So you get a remainder of 0, which is a multiple of 4. So same pattern over and over. All right, so for simplifying powers of I, rewrite the expression using properties of exponents, and then substitute I for I to the 1st power, -1 for I squared, -I for I cubed, and 1 for I to the 4th. All right, let's do this. So for the last example we have here, there aren't any extra practice ones, so we're just going to do example 6 from the book. For I to the 8th power, you want to think about how we can break down I to the 8th as multiples of 4. I to the 8th is I to the 4th power squared, okay? Because 8 is 4 times 2. We know that I to the 4th power is equal to what? 1. So this would just be 1 squared, which is 1. Again, if your exponent is a multiple of 4, it's going to be equal to 1. Right? What if it's not a multiple of 4? I to the 30th power. We can write this as a multiple of 2. 30 is 2 times 15. So we can say this is I squared to the 15th power. I squared is equal to -1. And then we know -1 to the 15th power would be -1. So we can use properties of exponents to simplify and rewrite this. Now these worked out nicely because 8 is a multiple of 4. Cool. 30 is a multiple of 2. Cool. Next one, I to the 57th power. Is 57 a multiple of something we know? 57 is 3 times 19. But that's not something that would jump out naturally to you. Maybe you can also say, well, this is 56 times, or 56 plus 1. And then we know 56 is even, so that's a power of 2. There are a few different ways you can break down 57. Figure out the way that's easiest for you. I'll show you 2 ways to do this. We could say 57 is 3 times 19. I to the 3rd power is -I. And then if we have -I to the 19th power, well, now we have to simplify this a little bit more. -1 to the 19th power. Yeah, maybe this wasn't the best way to do it because we have to do the process all over again. We can break this down as this is -I to the 18th power times a -I. Okay. -I to the 18th power is -I squared to the 9th. This made it a little bit more complicated, so I'll show you another way that's a little bit easier to do this. -I squared is the same thing as I squared, which is 1. But that's getting -I, and I don't think that's the right answer. Sorry. -I squared would be, -1. So that's -1 to the 9th times -I, which is -1 times -I, which is +I. All right, that is the correct answer. That's a longer way to do it, though. If we would have broken this up like I did here from the beginning, that might have been a little bit quicker. So option B. Or another method, you could have said I to the 57th power is I to the 56th power times I. Okay, and then we could have broken up the 56th power just like I did the 18th power there. That would be I squared to the 56 is 2 times 28. So you can say that that's I squared to the 28th power times I. We know that I squared is -1. So -1 to the 28th power times I. -1 squared is, -1 to the 28th power is 1. And 1 times I is I. All right, last one. Ooh, a negative exponent. I to the -20th power. All right, we just said that we want to try to make this some kind of multiple of 2. -20 is 2 to the -10th power. Okay, so this would be I squared to the -10th power. I squared is equal to -1. So -1 to the -10th power. And -1 to the -10th power. Oh, 10 is even. So that would be a +1. If you're thinking, oh, negative exponents, am I going to get 1 over something? This would be 1 over -1 to the 10th, which is just 1 over 1, which is still 1. So you can write it that way as well, if you wanted to.